Hi, everyone. Today's lesson, we're going to work our way through talking about the concept of rotation angles. And so what we're going to address today is a different way to create angles and a way that isn't tied to triangles. Now, triangles can become a component of rotation angles. However, what we're going to do is we're going to look at creating angles in a completely different context. And so, with that, we've got a bunch of terminology that we need to go through. So the first thing we can do is we can create angles at the origin. And we know to create an angle, that means you need two rays. And so one of our rays will lie on the positive x-axis. Now our second ray is also going to lie on the positive x-axis. And at the beginning, when both your rays lie on the positive x-axis, that's referred to as standard position. So quite often you're going to be asked to find an angle from standard position and blah, 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 blah. That's what that means when we hear standard position. Both our rays start on the positive x-axis. Now, both of those rays are actually referred to as arms. And so, if I get rid of that last arm, and we simply said, my first arm is going to lie on the x-axis. And then I'm going to take the other arm, which would begin on the positive x-axis as well, and I am going to rotate it to a certain position. So maybe I rotate it there. Those two arms then also have some different names to it. The arm that starts in the starting position, which in standard position would be on the positive x-axis, is referred to as the initial arm. And then the arm that rotates is the arm that's referred to as the terminal arm. The reason it's called the terminal arm is that to create an angle, that arm's movement must end, or it must terminate. And so it will end in a certain position, hence the terminal arm. When we rotate the terminal arm, the initial arm stays where it lies. It's stationary, it does not move. And through the rotation of the terminal arm, we end up creating an angle. And so in this instance, maybe that's angle theta. And so you'll notice that at the origin and between our two arms, we have created an angle. Now, just for argument's sake, let's say that we were going to call that angle theta 30 degrees. Then we would have then created an angle of 30 degrees between our two arms. Hopefully that makes sense. My picture is maybe not quite as proportionate as what it should be. However, that should end up giving us an idea of how we can create an angle. Now, that also means that I can create any angle that I like by rotating my terminal arm. And so, perhaps at the very beginning, I'm lying in standard position, and I then chose to rotate my terminal arm to that position. Well, I can tell that I rotated greater than 90 degrees because I got into the second quadrant. So I went my 90 degrees plus some extra. And let's just say that that extra I went was like 60 degrees. Well, my 90 plus my 60 would tell me that in this instance, that angle theta would equal 150 degrees. And so I can start to create angles that are larger than 90 degrees. More importantly, I can create any angle. So maybe this time I rotate my terminal arm all the way around into the fourth quadrant. Well, maybe I label that angle alpha, just to give it a different label. Well, for me to get into the fourth quadrant, we should be good that you would have had to rotate 90, 180, 270, and so I'm going to be somewhere between 270 and 360 degrees, a full rotation. And so maybe if we went, 45 degrees farther, we were exactly in the middle of the fourth quadrant, then that angle alpha would be 315 degrees. There is a way for us to be able to go through and create any angles we can. Now, I'm going to get rid of all of those angles that we just put on that set of axes, and I want to look at another way for us to be able to create different angles. So you'll notice the one quadrant that we maybe didn't put an angle into, quadrant 3. For me to rotate right now, I can start on my positive x-axis and rotate into quadrant 3. Let's say that I went 60 degrees into quadrant 3. There's my terminal arm lying in that position. I would have then went 90, 180, plus an additional 60 degrees. That's going to make that angle, where maybe I call it theta, 240 degrees. I can get my terminal arm to lie in that same position by going in a different direction. That I could also get my terminal arm to lie in the third quadrant in that exact same position if I chose to rotate in this direction. Now, how do we tell those directions apart? Well, in that instance, for me to rotate, maybe I call that alpha. That alpha then would be 90 degrees and another 30 degrees, and that would be 120 degrees. Now, for us to talk about rotation angles, you can see that if I was to just give you information and tell you that I wanted you to rotate beta, and beta is going to be 120 degrees. Can you see, given my diagram that I have, that could be a little confusing? That some people may follow the red rotation direction, and therefore angle beta would put our terminal arm in the second quadrant. Or maybe we follow the green rotation, and that would put our terminal arm in the third quadrant. So universally for us, we have to come up with the same language to make sure that our terminal arm ends in the same position always. And so how can I tell the difference then between my directions of rotation? We can use positive and negative angles. So my red rotation direction is actually a positive direction. And the way you can think about that is we know that we start in our initial position on the positive x-axis, and I begin to rotate my terminal arm up. And generally we go then, well, if I move up on a grid, I'm moving in a positive direction. That way, if we then address the green rotation direction, we know that we start on our positive x-axis. And for me to rotate in the green direction, that means that I would begin by rotating my terminal arm down. And for us, down on a set of axes means negative. And so really then what I have is I have that alpha is actually negative 120 degrees. So there we go in terms of positive and negative angles. Now, the last thing that we need to put in terms of some terminology dealing with rotation angles, is the concept of something called coterminal angles. And what you'll actually see on the diagram for us right now is theta and alpha are actually coterminal angles. And what those are angles that have your terminal arm finish in the same position. So you'll notice that if I rotate a positive 240 degrees or a negative 120 degrees, my terminal arm will lie in the same position. And therefore, those two angles are coterminal. Now, the important part for us, there are infinitely many coterminal angles. We may look at this at the very beginning and kind of say, but I don't see how I could get my terminal arm to lie in that same position any other way. And what we're kind of missing out on is the idea that we're not limited to one rotation. So if I was just to get rid of a little bit on those sets of axes and say instead what I'm going to do is I'm going to start in my initial position and I'm going to rotate my terminal arm a larger angle, then what I may do is I may rotate all the way around one full rotation. So we know just to get back to that initial position means that maybe this is now angle beta. Then what I've done is I've already gone 360 degrees for my one full rotation. And now what I do is I rotate around another 240 degrees to put me in that same position. And so if I deal with my full rotation plus another 240 degrees, then that's going to actually get me an angle of 600 degrees. Beta would then have me rotating 600 degrees. It would be coterminal with the other two angles. Any angles that have your terminal arm lie in the same position are referred to as coterminal angles. So there is a bunch of terminology to get things started for today. What I want to do now is I want to break down some movements within that set of axes so we can start to look at some other concepts that are going to arise. So let's jump back to a clean set of axes now, and what we're going to do is pretty quickly we're going to go through and we're going to put on that first quadrant angle. And I'm going to tell you that when we just rotated that theta, whatever that angle is, I'm going to be specific and say that that's 30 degrees. Now, what I want to do is I want to create a bigger angle. Let's start getting out of the first quadrant. And what we're going to do now is we're going to rotate all the way around into the second quadrant. And we're going to say that that angle measurement, which we'll call alpha, was 150 degrees. What I need us to do very quickly is to see that my theta angle of 30 is directly related to my alpha angle of 150. Now, we may look at that and we may not see how they're related. So what I'd like you to do is just take out your calculator and we're going to push some buttons to get some very quick trig ratio calculations. So what I'd like everybody to do, whether you need your calculator or not, I want you to find the value of sine 30 degrees. I'm hoping most of you know what the value of sine 30 is, given our work on special triangles. You're getting a little confirmation right now that we get a value of a half or 0.5. At the same time now, what I'd like you to do is I'd like you to punch in what the sine of 150 degrees is. And what we're going to notice is we get the same value. Now, because we get the same value for those, then we should see that there's some sort of relationship between a 30-degree angle and a 150-degree angle. We got the exact same sine ratios for both of those. Perhaps you can see on your diagram right now why those two angles are related. For us to be explicit in that, what we're going to do is we're going to put on a little bit of information in our diagram, and we're also going to introduce some new terminology. You might see the relationship between those two because you notice that when we rotate 150 degrees, we actually create this angle in here. That's an angle formed between the x-axis and your terminal arm. And that angle that we just formed would be 30 degrees. You can see that if you went all the way around to the negative x-axis, you would have went 180 degrees. And so by rotating 150 degrees, we were actually 30 degrees short of the x-axis. Maybe now you can see why a 30-degree angle is related to a 150-degree angle. In fact, that angle that we have in there, and we're just going to call that one beta, is actually referred to as the related acute angle. And sometimes you'll see that just jotted down as like your RAA. Your related acute angle might be one of the most important things that we can find when we deal with rotation angles. Key thing, your related acute angle is always formed between the x-axis and your terminal arm. Also, one last thing. Please don't let the direction of the arrow put on beta make you think, oh, wait a second, I was rotating in the other direction. Isn't that negative? Related acute angles are always positive. Always. And so, if we can introduce that kind of terminology for us, then I think we're doing really well. We now understand at this point how to rotate in a positive direction, in a negative direction. We know how to make a terminal arm lie in a certain position, and we also have the ability to come up with a related acute angle. So I'm just going to get rid of all of that writing on the bottom now because we're a little bit better. We know what a related acute angle is. And if I was to say, then I would like you to rotate an angle measurement of 305 degrees. So we're going to call our angle measurement x 305 degrees. Then we should be able to put on our terminal arm. So what I'd like you to do, pause the video, put on your terminal arm. Okay, we're back. So I'm rotating in a positive direction, so I have to begin going up. I'm then going to rotate 90, 180, 270, and now for me to get up to 305, that means that I have to go 35 extra degrees into the fourth quadrant. So this angle x then would be 305 degrees. So I now need you to go ahead and label on your related acute angle. So right now, put on your related acute angle. Okay, we should be back. And so what we can take a look at then is, if I was going to do my full rotation, then I know that I just rotated 360 degrees. My angle that I've been asked to rotate in is 305 degrees. That means for me to get my related acute angle, I'd have to take that 305 away from my 360. That's going to leave me with maybe angle y as my related acute angle of 55 degrees. Okay, you'll notice then that I've been talking about angles over and over and over again, and we kind of have different terminology. So in this last instance, we found that my 305 is related to my related acute angle of 55. For us to introduce kind of that new terminology then and make sure that we're just good on that terminology, that angle x would be referred to as your principal angle. That's the angle that's created that determines the ending position of your terminal arm. My y is then the related acute angle that goes with that. There we go. So now we've introduced related acute angle as some terminology as well. We're really starting to build up on some stuff. Okay, hopefully we're good to that point. Now I want to keep rotating around our axes. Okay, so what I've done is I've just cleaned up our axes a little bit. And now what I want to do is I want to rotate into the third quadrant. And what I'm going to do is I'm actually going to rotate into the third quadrant based on the previous two angles. So for me to rotate into that third quadrant, but have the same related acute angle of 30 degrees, means that my principal angle is going to have to be 180 degrees plus the other 30. That means that maybe that green angle, if I was to call that beta, is going to be 210 degrees. Okay, we can see how they're all related because they all have a related acute angle of 30 degrees. We all know that the sine of 30 degrees is 1/2. What I'd like everybody to do is push some buttons on your calculator and come up with what the value of the sine of 210 degrees is. Okay, there are two big things that can come up, two big ideas from the fact that you end up getting a value of -1/2. Okay, the first one, and please don't overlook this. You just pushed a trig button. You know that in trigonometry, sine means opposite over hypotenuse. And you did that for an angle of 210 degrees, knowing that you could never construct a triangle that has an angle of 210 in it. So the first thing that we should notice is you got an answer when you punched in sine 210. That tells you that we can calculate trig ratios for angles that don't even fit inside of a triangle. That is a huge concept for us moving forward. The second thing that we should notice, you got a half again. However, you now got negative 1/2. Perhaps some people might be able to try to figure out a little bit, and they could kind of reason out why, when you calculate the sine of 30, you got 1/2. When you calculated the sine of 150, you got a half. But now when you calculate the sine of 210, you got negative 1/2. Why the sign of that ratio all of a sudden changed to a negative? When we take a look on our diagram pretty quickly, I'm hoping that we can maybe kind of come to one big idea. Notice that in that blue angle of 150, I am still going up from my x-axis to get to that terminal arm. Maybe you came up with a reasoning then for why your sine is positive, because you're up. And therefore, when you take a look in the third quadrant, for you to get to that terminal arm, you had to go down, and therefore going down would imply negative. If we came up with that justification, we're doing great. But it doesn't really have the whole idea to it. So what I want to do is I want to add in 2 more ratios. And all we're going to do is we're going to stick in quadrants 2 and 3. Right now on your calculator, I'd like you to calculate the cos of 150. And I'd like you to do the same thing and calculate the cos of 210. And when you do that, you're going to notice that you get a big, ugly decimal. More importantly, when you calculated the cos of 150, your reasoning may have been challenged. We would have noticed that you got a negative value. And so your reasoning of, yeah, but we went up to that, just got challenged, because up should be positive, and therefore you have a cos ratio that's negative. Those two ideas maybe don't mesh. You then balance that against dealing with a cos of 210, and you notice that your cos of 210 is also negative. Okay, and now how do we gel all these concepts together? Well, I'm going to put one other arrow on our diagram, and I think that might help you. So to do that, I just want to clean up a little bit of what's on our current diagrams. And what you're going to notice is I'm going to put in a dotted line. That on that blue triangle, I can actually construct a right triangle. And it's a right triangle for my related acute angle. And based on that related acute angle, I now have an opposite side, I have an adjacent side, and I have a hypotenuse. And for us to then look at the sine of 150, if we were to have a side that went up, then it should make sense that up is going to be positive. Secondly, though, that's not going to gel for the cos. But if I put on one more arrow to say that my adjacent side would then have to go to the left. And if we look at moving to the left on our set of axes, we should see that my adjacent side is actually going to be a negative value. And so, if you were to examine then cos, well, cos is going to be adjacent over hypotenuse, you are now taking a negative value as you move to the left. that's going to gel with why your cos creates a negative ratio. You'll also see the same thing then when we move it down into quadrant 3. When I create my triangle, I'm moving down into the third quadrant, and therefore my opposite side is negative. We got confirmation with that on our sine ratio. But notice you are still moving to the left to get into the third quadrant, and left means negative. And so my adjacent is negative, and therefore my cos is also negative. So we're going to add in a little bit of direction to the way we move to create our terminal arm. And so what I want to do is I want to now look at all 4 quadrants. And so as we take a look at all 4 quadrants, you'll notice that I have all 3 primary trig ratios listed in all 4 quadrants. What all I want to do is to go through and examine what is the sign of each one of those ratios in each quadrant. So let's start off with that first quadrant, and I'm going to rotate into the first quadrant anywhere. For us to examine what sign those are, we're going to have to think about building a triangle. And to build a triangle means I'm going to have to go over a certain amount, and I'm going to have to go up a certain amount. That's what puts me on the terminal arm. Now, I jump back into viewing this as a Cartesian plane, a set of axes. And if I were to move to the right on my grid, then I'm moving in a positive direction. If I was to move up on my grid, I move in a positive direction. And so for me to calculate the sine of any angle that puts me in quadrant 1, I would now calculate sine being opposite over hypotenuse. That means that my opposite sine is positive. Don't really know about my hypotenuse yet. Cos is going to tell me to calculate my adjacent over hypotenuse. And so when I calculate adjacent over hypotenuse, I have a positive adjacent side. And now when I get to tan, that's going to be opposite over adjacent. I can at least put some signs on each one of those coordinates. Okay, the only thing I'm missing is my hypotenuse. And a nice way to think about your hypotenuse is since your hypotenuse is always on a diagonal, it doesn't have a sign. And we know then that numbers that don't have signs can be treated as positives. And with that information, I can now complete my sine and my cos ratios. And so when I calculate a positive divided by a positive, that's a positive. A positive divided by is a positive, and a positive. And now what I'd like you to do is I would like you to pick any angle that is greater than 0 and less than 90, an angle that would lie in the first quadrant, and calculate your 3 trig ratios based on that. And we'll see that each one of those 3 are all positive. So now what I want to do is I want to move us into the second quadrant. So if I have an angle that puts me in the second quadrant, we can kind of look at it in a different direction. If that angle was called theta, then my range of theta, I know that that angle would have to be greater than 90 degrees, and it would have to be less than 180 degrees. Okay, for me to get a point anywhere along that terminal arm, or to get that terminal arm into that position, I would have to move to the left, and I would have to move up. Well, I know that left movements on my axes are negatives, and I know that upward movements are positives. And so for me to go through and calculate then, well, what is the sine? Sine is always going to be opposite over hypotenuse. And since I'm incorporating hypotenuse, I know my hypotenuse is always positive. So my opposite over my hypotenuse is a positive over a positive, which is positive. But now when I calculate my cos, I know cos is adjacent over hypotenuse. My adjacent side is negative, while my hypotenuse is positive. And so when I calculate that, I get a negative value. You may also see then why the tan of any angle in the second quadrant would be opposite over adjacent gives me a negative value. Now, we haven't calculated the tan of any angle up to this point, so pick any angle that lies in the second quadrant, punch it into your calculator, and notice that you're going to get a negative value for your tan. Okay, we can pick up the pace and we can move. So what I want you to do is I want you to pause the video right now and try to come up with the signs of each one of your trig ratios in quadrant 3 and quadrant 4. Okay, we're back. And so we can go pretty quick. Any angle that puts me into quadrant 3 has to be bigger than 180 degrees and less than 270 degrees. So for me to get into quadrant 3, I have to move to the left and I have to move down. Those are both negative movements. I know that my hypotenuse is always positive. So for me to calculate my sine ratio, I need opposite over hypotenuse, and therefore that's going to give me negative. For me to move or calculate my cos means adjacent over hypotenuse, and when I do that, I'm going to get a negative. And maybe something that would be surprising to most of us. If I was to calculate my tan, that is opposite over adjacent. That's a negative divided by a negative. So I want anybody, pick an angle in quadrant 3, punch it in, confirm that you get the signs of those ratios. Now moving into quadrant 4, any angle in quadrant 4, if we're rotating in a positive direction, must be greater than 270 and less than a full rotation, 360. For us to calculate into that quadrant means I have to move to the right, which is positive, and I have to move down, which is negative. So my sine ratio is going to be opposite over hypotenuse, which is always positive. Therefore, I get a negative sine. My cos is going to be to the right, which is positive, over my hypotenuse, which is always positive. And my tan has to be opposite over adjacent, and opposite over adjacent is different signs, and negative. So what we did is we just rotated around all 4 quadrants, and we now have the ability to figure out what sign would each trig ratio be if my terminal arm lied in any one of those 4 quadrants. Okay, what I want to do lastly is I want to kind of jump into our 4th quadrant and just examine another scenario you're going to find yourself in. So what you'll notice is I'm kind of focusing in on the 4th quadrant right now. And so I've drawn my axes so I have a lot of room to work in the 4th quadrant. What I want to deal with this time is a little bit of a different information. That rather than me telling you what angle we're going to rotate to lie in here, I'm going to give you information about what point we want our terminal arm to pass through. So I'm going to ask that our terminal arm passes through the point, and I'll just call it point P, 5, -3. And so we should all be good that to come up with that, point P at 5, 3 means I have to go across a lot and down a little bit less. So maybe there is point P. If point P is at 5, -3, then my terminal arm would pass through that like such. Okay, couple kind of questions and a process that we're going to kind of go through. The first thing that I'm going to ask you to do is I'm going to ask you to come up with the values of the sine, cos, and tan for that angle. So for us to rotate, I'm going to define it that we have rotated in the positive direction. We're going to call that angle theta then. And so what I'm asking you to come up with is the sine of theta, the cos of theta, and the tan of theta. So we know that to come up with what those actual ratios are, now we need a number to them. That means we need a triangle. And the way that we can always produce our triangle is to create our triangle with the x-axis. And so what we're going to do is we're going to drop in a height from the x-axis. I'm dropping it in. It is a height. That means that it intersects the x-axis at a right angle. And as soon as that intersects the x-axis at a right angle, we then have the ability to create our right triangle and label those sides. So, since that terminal arm passes through the point 5, -3, I actually know the side lengths on my right triangle. For me to get down to point P, I must have gone across 5 and down 3. And by doing that, I've been able to label the two smaller sides of my right triangle. The only thing I'm missing is my hypotenuse. And we can jump back into grade 8, and we can go through and we can find the value of the hypotenuse using Pythagorean. So c squared is going to be 25 plus 9, c squared is going to equal 34, and c is going to exactly equal root 34. So I can now label that on my triangle. Now that I have all three sides of that right triangle, I have the ability to label all three trig ratios, or find the value of all three trig ratios. So for me to calculate the sine of theta is going to tell me opposite over hypotenuse. There you go. The exact value of your sine ratio for theta. Now, we also look at that denominator, root 34. It cannot be simplified. But also, since we've been asked to just list the ratio, you don't have to worry about rationalizing the denominator. You can if you want, but you can leave it with the root on the denominator. Now we can go through and find the other two. Pause the video if you can see it, jump ahead, and we'll see if we match up. Now that we're back, we should see that my cos has to be adjacent over hypotenuse, and my tan has to be opposite over adjacent. There we go. So that's going to give us the ability then, if we know any point that a terminal arm passes through, we could create the right triangle, and we could go through then, and we could determine those ratios. Now, I just want to make a step back for a second, and I want you to notice that there's one key feature that we did not label on the diagram. I'm going to label it now. There may be some people that are saying, but wait a second, the angle inside that triangle is actually alpha, the related acute angle. And so when I just found all those blue trig ratios, wasn't I really finding it for alpha, not theta? And I just want to draw to your attention one important thing. What type of angle is alpha? It's an acute angle. And if I was to ever rotate an acute angle, what quadrant would I be in? Quadrant 1. And so if I was to go into quadrant 1, I know that all my ratios are positive. So if I wanted to find sine alpha is positive 3 over root 34. Cos of alpha is positive 5 over root 34. Tan of alpha is positive 3 over positive 5. You might be able to see why the blue ratios are your correct ratios. What those blue ratios have with it is they have the signs that dictate the location of the angle. That if you look back at your previous set of axes, there's only one quadrant where your sine is negative, your cos is positive, and your tan is negative. And that's in quadrant 4. And so by listing all three of those ratios, you're actually finding the ratios for theta that put you in quadrant 4. You're not finding the ratios for alpha. That's an acute angle. Okay, lastly, what I want to do is I want to make a step back then, and let's go through and find the other two features on that diagram that are still unknown. We don't know what the angle measurement of theta is. We just know the terminal arm passed through a point. And we also don't know the value of the related acute angle. But we can use the related acute angle to find theta. So I'm just going to get rid of all of this writing that we did here that's not needed. And I want to jump back into what we have. For us to go through and find the principal angle, we need to find the related acute angle. And so I'm going to focus in on alpha. Because given alpha, I have my right triangle. Now, I want you to notice that I'm going to put a star beside your tan ratio, because your tan ratio is going to be an important ratio for us. I want you to notice that your tan ratio included the least amount of work for you. Your tan does not include your hypotenuse. And so you didn't need the hypotenuse. And so if you made a mistake finding the value of the hypotenuse, you wouldn't now compound your mistake by using an incorrect value. You can get your tan directly from your coordinates of your point. That your tan ratio is actually always your opposite, so your y coordinate, over your adjacent, your x coordinate. By using that feature, and also using the fact that your related acute angle is always positive, then we can work backwards to find alpha. We know that alpha then would have to be the inverse tan, for us to go backwards and find an angle, of 3/5. Now I just want to stop there for a second, make sure that we examine something closely. Notice I didn't put -3/5. The -3/5 would have been what put me in quadrant 4. The +3/5 gives me my related acute angle. Remember, all related acute angles are positive. And so if I was to go through then and push some buttons, you could come up with a decimal approximate for what alpha is. Go ahead and push some buttons, see if we match up. Okay, we're back, and hopefully if we rounded to the nearest degree, you found out that angle alpha is 31 degrees. Now that we know what alpha is, we can now work our way backwards and we can come up with what the principal angle theta is. You know that if alpha is 31 degrees, then theta has to be 31 degrees short of a full rotation. And so I would be all the way around 360 degrees less the 31 degrees, which means I should get 329 degrees as my angle measurement for theta. So we're going to wrap it up there. We threw a ton of new terminology at you. And then we worked through some trig in a little bit of a different way as we learned that we can start to use trig for angles that are bigger than 180. Your job now, get comfortable being able to put a terminal arm in its finishing position, being able to deal with terminal arms that pass through points. Okay, jump in and get some practice. Good luck.